Okay, in this lecture, we'll go through arc length and curvature. So, arc length is actually a topic that you should have covered in Calc 2, and we're just generalizing this up a dimension as well. So, here, well, and we're introducing like vector notation to talk about it. So, here we have a curve C that is defined by this vector valued function, R, with component functions f and g of t, where t runs from a to b. And then we want to um, have a way to calculate the arc length of the curve over the interval. Well, there's this integral that we can perform, where what we do is for each of the component functions, we take their derivatives, we square them, we add them together, and then we take the square root, and then we integrate that resulting function from a to b. So it's probably been mentioned in your previous class, Calc 2, that the arc length function, this type of integral is difficult to compute usually when you have a square root inside. You need like the inside to collapse to simplify significantly, or otherwise you end up with an integral that you can only like do numerically. And we'll see how problematic it can get. Okay, but I want to mention this. There is some intuition behind this, which also probably should have been mentioned when you took Calc 2, but this formula, the reason it makes sense is because it's basically because you're doing the Pythagorean theorem on each of the infinitesimal pieces. So say that you started at this point here, and then you traversed one time step, and then you ended up here. What you could do is measure how far it changes in the x coordinate, well, I'm sort of indicating the y coordinate, how far it changes in the y coordinate and in the x coordinate. But then the overall change of distance, which some people might reference as ds for a differential element of arc length, this change in the distance between the 2 points is actually given by Pythagorean theorem, right? You have a dx, well, dy there, you have a dx there. What you would do to compute the ds is you'd square the dx, square the dy, sum them together, and then take the square root to get ds, which is basically what this is doing here. And then another thing you can notice is that, well, this expression inside is actually this magnitude of the derivative of this vector function. Now that we've introduced the notions of the derivative of a vector function and magnitude, you can see that these quantities are identical. And then what we can do is lift this up a dimension. In fact, we can probably lift it up to arbitrary dimension, but we only really need to concern ourselves with dimensions 2 and 3. So in dimension 3, we would have an additional function for the z position, and everything it generalizes in a rather straightforward manner, right? We have the three-dimensional distance formula here, and that can also be thought of as you're taking the magnitude of the derivative of the vector function r. And maybe one thing to mention is that these curves have particular names, although I probably won't use them very frequently. So a curve that is stuck in 2 dimensions is called a plane curve. A curve that exists in 3 dimensions is called a space curve. Okay. But the fact that we're talking about a curve means that the object itself is one-dimensional. This kind of comes into play when we will talk about surfaces in, I think, the next lecture. So curves are one-dimensional objects, but they might sit in like 2-dimensional space or 3-dimensional space, as you can see. But the intrinsic object itself, the geometric object, is one-dimensional. If you're like a point on that object, you can only vary in one like axis, one dimension. All right. So let's see an example. So here we're given a curve defined by this vector function, and we want to find the arc length parameterized by this curve from t equals 0 to 2 pi. So the process is to compute this integral. Right. So first we start by taking the derivative of this, and you'll notice that this requires us to use product rule, so it's a product of two functions involving t. So product rule for the first function gives you this. Product rule for the second function gives you this. And then third function is pretty easy to differentiate. Next, you have to take the magnitude. And now this is where things have to work rather nicely. You want the function to simplify. And so in this case, it does. When you square these things out, the middle terms end up canceling, which is what I've indicated here. And then, let's see, cosine squared plus sine squared is equal to 1, and you have that kind of show up here with the t squareds as well. So you can factor the t squared out of these two terms, and then sine squared plus cosine squared is equal to 1, so that just becomes t squared. So you end up with a t squared plus 1 plus the 4 at the very end, giving you a t squared plus 5 in a square root. So the integral that calculates arc length becomes this from our calculation of the magnitude of r prime. Okay, it becomes this integral. Now, if this was a live class, I would challenge you guys whether or not you know how to integrate this thing. Because this technically, if you passed Calc 2, then you would know how to integrate this. But it is a somewhat challenging integral, and it is tedious, as I say here. So I've sort of spoiled it for you down below. There is a general formula for doing this, but typically it is a bit of a hassle to show you why we know this, how we know this, and certainly is something that we have to kind of talk you through when we do this kind of class in person. So let me, the fact is that like I have actually done this in previous renditions of teaching Calc 3, so let me pull up that document that I've hyperlinked. So yeah, if you are looking at this at a later time, you can click on that link, or I guess type it in, although it's a bit of a bother to type it in. But you can do that, and then you'll end up with this document, which derives for you the. Let me hide that, and maybe I'll just full screen the PDF. So let's talk through this, and if you are not interested in the derivation, then you can skip ahead because this is a video recording, right? So the derivation is you have this kind of expression here, and what you have to recognize is that this is the perfect form for a trig sub. In particular, you want to use x is equal to tangent of theta. I'm using theta here. You could use u instead. But because of this trig sub, you end up with an a squared that you can factor out, and then this tan squared plus 1, which by Pythagorean trig identities, you should recognize this is equal to tan squared. And then, of course, to complete the trig sub, you have to replace the dx. So take the derivative of both sides of this, and you get a secant squared theta d theta. So the trig sub gives you this new derivative, and then you can take the square root of the a squared, giving you a times a, so a squared comes out. And then this becomes secant squared, yes, in the square root, so then you end up with secant cubed. Right, so now this ends up becoming a bothersome trig integral, integral of secant cubed, which in Calc 2, you probably learned to do this using a trig reduction formula. Below, I go through a different way of doing it, which shows you how to do it directly using integration by parts, which I'll talk about in a minute. But let's sort of just take for granted that we know integral of secant cubed is this expression here. After that, what you need to do is back substitute, undoing the trig sub. So the process is that, well, this trig substitution corresponds to this triangle, right? Where we have, if I divide a to the other side, then we're saying that tangent of theta is x over a. That gives you a relationship on the sides, the ratio of the sides. So opposite over adjacent is x over a, and then the hypotenuse is something you can derive through Pythagorean theorem. And then you can sub everything in, so we can read off of the triangle what secant theta is supposed to be. So secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is going to be the reciprocal of that. It's going to be hypotenuse over adjacent, which gives you this fraction. Tangent, you can just read off by dividing over, and then secant and tangent again. And then there's some more algebraic simplification, so let me just briefly talk through that. So I distribute the a squared across. That's going to cancel these two a's here, and I just kind of collect this together. This first term I collect together to give me this. Next we have, yeah, this term, nothing really happens to that. I'm just combining the fractions. But then I do something just to clean this expression up a little bit. So this division inside the logarithm can be subtraction outside of the logarithm, one of the log properties that we have, right? So multiplication becomes addition. Multiplication inside becomes addition outside. Division inside becomes subtraction outside. So you end up with this, and I just distributed the a squared over 2 to both the terms of the log. And I'm specifying that this gets absorbed into the constant of integration, so we can just make that disappear because that is a constant. A is some specified number that I just haven't specified, but it would be a number, so this is just a constant, and you end up with this expression. Now, coming back to this thing that I sort of waved over, how do we do integral of secant cubed? Well, it's a somewhat tricky trig integral. What you do, if you aren't just given the reduction formulas, is you have to recall that it's a weird thing involving integration by parts, and you need to kind of separate it up in a clever way. I don't find it completely intuitive to do this. So, let's see. Well, you break one part of it to secant, you break the other part into secant squared, and then you choose one part to differentiate, the other part to integrate. Right? That's how you do integration by parts. It's integral of u dv equals uv minus integral v du. Some of you might have learned it using f's and g's instead. The lucky ones of you will have learned tabular integration, but I'm not going to go into that now. So instead, we'll just talk about it using u and dv. So you separate it out. U is the part that you differentiate, dv is the part that you integrate, and what we can easily do is integrate secant squared, because we know that that is tangent. So we force that part to occur, and then we end up having to take the derivative of secant. Okay, and so by integration by parts, we know that this integral is equal to uv, which is secant tan, minus integral v du, which is, when I collect this bottom row, ends up being tan squared secant that we have to integrate. And then we can relate this back to secant cubed. So this kind of becomes a cyclic by parts problem. Using the trig identity, tan squared plus 1 equals secant squared. Moving the plus 1 to the other side, we get that tan squared is equal to secant squared minus 1. And so we get this. Next, we distribute, and then we notice that we have this guy, right? The problem that we started with. So I can move that to the other side, and we end up with 2 copies of the original problem, the original integral of secant cubed. 2 copies of secant cubed, integral of secant cubed, is equal to secant tan plus the integral of secant. And then, well, at this point, you would kind of just have to know this fact that integral of secant cubed is ln of secant plus tangent. There is a way to show that. It involves knowing a clever trig property to kind of force it to look like secant plus tangent on top and on bottom, like to make it fit the format of being an ln problem. You've probably seen the derivation of it. It's not a completely obvious thing either, but taking that as a fact, you would have ln of secant plus tan, and then you'd have to divide both sides by 2 to arrive at this identity. So integral of secant cubed ends up being this expression, which is what we used up here to evaluate this integral and to do the back substitution. So if you didn't have this formula, which, I mean, the book kind of mentions it in one of its examples, but it kind of references, like, see the table of integrals at the back of the book. If you didn't have that, then you'd have to kind of run through this process of deriving it. Most likely you'd be given something as terrible as this. Anyhow, let's come back to Calc 3. So we were just doing Calc 2 because we needed a brief diversion to explain how we do this. So you'll notice that this is in the format of this kind of integral, right? X's have been changed with u's in this case. But in our problem, we have t is u, and 5, well, it should be square root of 5 is a. So when you plug things in, well, it only shows up, a squared only shows up, so a squared gets replaced with 5 everywhere. And so we're just applying the formula, it looks like, yes. We're just applying the formula, and then we evaluate it at the two endpoints, at 2 pi and at 0. Well, at 0, it's pretty nice, I think. Everything collapses except for this ln at the end. You end up just with root 5 inside the ln, which is this part. 2 pi, everything pretty much sticks around, so you end up with this nasty expression. And this is what I've boxed, because this is what you would want to see as a math person, but I guess as an engineer person, perhaps you shouldn't have a period there. But as an engineer person, maybe the numerical quantity is more intuitive for you. Either way, I especially called this problem out because your problem has your 102. I think it was this number. You end up with an integral that's quite like this, if I remember correctly. So you will be using this formula. Okay, continuing on. So arc length parameterization. So this is something that it's not mentioned on your homework directly, but this is an important concept, and I know that this has been tested in previous runs of this class. So basically, the idea is that, well, the way that you parameterize a curve, it kind of depends on certain things that you don't want it to depend on. So for instance, let me just like try to mark. You can imagine that like every second or so, like you could have a particle traveling on this curve, and every second or so, maybe you see it's in this position, then this, then that, then that. The tick marks are indicating position. Well, I could have a completely different parameterization that is like that, where the particle ends up slowing down a lot, right? This would mean that the particle has somehow slowed down a lot because each second it ends up only traveling a tiny bit. And what we want, in a way, is when we talk about curvature, in order to get into discussing curvature, is we actually want a parameterization that doesn't depend on like the nature of the particle moving along the curve. We want a parameterization that only depends on the curve itself, on intrinsic properties of the curve itself. And the reasonable way to do that is actually to make it be that at each time step, quote unquote time step, that the particle has traveled the same length. In that way, it's like the particle travels at a uniform velocity along the curve. And so we don't have this oddity of like possibly making the particle speed up or slow down as it travels the curve. And so that's where this arc length parameterization comes into play. We sort of create this, and then that resolves the problem here. So the arc length parameterization, well, it's defined by this function. You can see that it's pretty much the same as, well, it's very similar to the formula for arc length. So instead, you introduce a parameter t that shows up in the upper index of your integral. And your integral, we use a dummy variable u to indicate that we're changing the variable inside the integral, but outside we have this parameter t. So the point is that this then gives us a function that when we plug in a time, it should give us a distance, roughly speaking. And so then we are able to construct from the parameterization that we start with, this r of t, this parameterization of the curve that kind of is based around time, we can convert that over to a parameterization that depends on length. Because when we take the inverse function of this, we'll go from a function going from time to length into a function mapping the other way around, from length to time. And then we can just compose So we do length to time, and then we plug that directly into the r of t parameterization, and the resulting composite function is a parameterization from s to position on the curve. Okay, so that is possibly confusing for some of you, but maybe this example should help to clarify what's going on. So, and I should also mention that this can only be done with particularly nice curves. I think it is only something that you can do with like helixes, in fact, or something as nice as this. Looks like this is a line. Yeah. Okay, so a line can also be done, but anything that is more complicated than that, I think there are issues with constructing the arc length parameterization. So, okay, so the process is we compute this integral. So you can see that first I take the derivative of the function r, then I take its magnitude, which ends up being a constant. Okay, very nice. Then we can integrate this. Why did that become 3? Ah, yes, because up here we're specifying that t starts at 3 and then goes to whatever arbitrary time. So integrating the function 3, we end up with 3u. We evaluate u from 3 to t. That gives us a function 3t minus 9. Okay. So then, so that gives us a mapping from time to length. Right? So at time 0, it has length 0. At time, or not time 0, time 3, it has length 0 because we start measuring length at 3. And then at time 4, it would have length 3. 12 minus 9, 3, yeah. So we end up with this kind of relationship, right, between time and arc length. And then solving, right, this is what I mean by taking the inverse function. Solving for the other variable, solving for t, we end up with this expression. So this is the inverse function. This relates arc length to time. And then what you can do is compose this, plug this into the formula for the parameterization. So the way we do that is we insert everywhere that we see t in this expression. We instead replace it with 3 s over 3 plus 3 to each of these functions, and that gives you this. Notice we don't do that for the outermost guy, the thing that's defining the parameterization of the curve. And simplifying, we end up with this. So now this is the arc length parameterization of the curve. So they define the same curve, though all the points will match up, but the way that the points are spread out may differ. Okay. All right. Now, why is this necessary? So this is necessary because of how we define curvature, but then we'll shortly see that we actually, for convenience, we will use different formulas for curvature. Okay. Well, first of all, what is curvature? So the notion of curvature is kind of the intuitive notion. It's how quickly does a curve, how quickly does a curve curve. Yeah. So in this picture, you'll see that it's less curvy here than it is here. And so you intuitively, you'd think that, well, the curvature here has to be smaller than the curvature here, right? The sharper the turn, the greater the curvature. If you think about it as like, if you're in a car and you're turning, well, how much do you have that, what is it, centripetal force? The stronger the centripetal force, the greater the curvature that your car is performing. Okay. So notice that in this definition, we are actually using the arc length parameterization. That is mainly why I was forced to mention the arc length parameterization above. It's because the way that curvature is defined is in terms of the function, the parameterization of the curve, but defined in terms of arc length, not in terms of time. But it ends up using this expression. So this t prime of s magnitude is how it's defined. And let's just think through what this actually would require us to do. So in a previous lecture, we discussed this. So this is actually the unit tangent vector. What you do to create this is you starting with a parameterization of a curve r of t. You take its derivative with respect to time. You then divide by the magnitude in order to normalize it, and this is tangent because it's pointed in a direction that is tangent to the curve. It's the direction of change. The fact that it's the derivative kind of makes that happen. But notice that this is t of t. This is the unit tangent vector parameterized with respect to time, not with respect to arc length. So in order to construct this expression, what you would have to do is actually start by reparameterizing your r of t. You'd have to create the arc length parameterization, r of s, then you'd have to compute t of s, which requires that you take derivatives of this function with respect to s, which I'm still denoting by a prime because it should be clear that this derivative is with respect to s, not t here, since our function is with respect to s. Then we normalize it, and that will be the unit tangent vector. And then you have to take that derivative, the derivative of that function, and then you have to take its magnitude. And so that is a painful process. I'm not sure what functions that is doable on. Maybe lines and helixes only. That might be the case. So it's quite tricky to work with this. So instead, what is rather standard to do is to then derive other formulas, which I'm not going to derive them. I'm just going to mention them and tell you that if you want to look at how they're derived, you can check a textbook. But the derivations are not very, they don't really explain too much. It's just a bunch of algebra, I believe. So okay, first one we have here. So this one's a little bit. Notice the difference. Instead of r prime and r prime, like in these expressions, we have a t prime and an r prime. But also conveniently, notice we don't have to reparameterize. We have t here. So what you can do is construct t of t, take its time derivative, and then you have to take its magnitude, but then divide by r prime, the magnitude of r prime, which is something that you would have computed in the previously, because that's something that you need to do to construct t of t. Okay, so that is one possible formula. This next one has some other reasons it can be useful. I'll show you an example where this one is better to use than the above one. So here we only need r and its derivatives. So starting with the function r of t, we would then take its first and second derivatives. You could cross the two because these are vector functions, so they output vectors. We could take the cross product of two vectors, then take its magnitude. In the denominator, yeah, so the first derivative, magnitude, gives you a scalar, cube it, and so this whole quantity ends up being just a number. Okay. And then here's an even more convenient thing that can happen. So if your function, or if your curve C is a very special function, is a very special type of curve, if it's actually a graph of a function, meaning that you can describe it as a function, y equaling f of x. Right, so for example, like a parabola would be a function like this. What is not would be like a circle, for example. So because this doesn't satisfy the vertical line test, this doesn't pass the vertical line test, so this is not a function per se, y a function of x. Right, so that is not the case, but this one is. So for special curves that can be described as being a function of x, and I guess, yeah, the derivative and the second derivative of that function exist, then you can compute the curvature at a point by using this expression. So you got absolute value of the second derivative. You probably should be plugging in at the point, plugging in at x, and same with the denominator, taking the first derivative, squaring it, adding 1, and then taking the 3/2 power. Okay. Right, so let's see some examples. So this first example, this is actually a very useful fact to know, and I ended up just sort of deriving it here. So a fact that some runs of this class emphasize is that the curvature of a circle of radius r is 1 over r. It's the reciprocal of the radius. So intuitively, you can think that, well, okay, if your circle has a smaller radius, it will have a higher curvature, right? If your radius is 1 versus 2, right? Circle radius 2 has curvature 1/2, so radius 1 has curvature 1, and so you do have the correct kind of relationship. That smaller radius gives you higher curvature. Okay. How do we derive this? So the way I worked through it is I end up using this formula, which is the first alternative formula that I've listed. So just it's I think it's a fairly straightforward calculation. So maybe a bit tedious, but yeah. So you take the derivative with respect to time. R is just a constant that we don't have specifically. So, you end up getting this when you take the time derivative. Then taking the magnitude, you see that sine squared plus cosine squared allows you to simplify, and then the magnitude is rather simple, just r. Then for the unit tangent vector, this guy, you end up dividing. So divide r prime by r, or well, r prime by its magnitude, which ends up just being r. So that will actually get rid of the r in front of both functions. So we have this as our unit tangent vector. And then taking its derivative with respect to time gives us this vector function. And lastly, for curvature, we take that t prime of t, take its magnitude, which is 1, right? So because when you take its magnitude, you end up taking the square root of cosine squared plus sine squared, which is square root of 1, which is 1. So that's the numerator. And then this r prime magnitude is something we previously computed. So we just get 1 over r. That's a pretty nice derivation for us. We can derive this neat fact. Next, problem that is similar to your homework problem. Is that right? So find the unit tangent vector for this given vector function. Now I can see right away this is actually a helix because of the x and y. So it's rather short, this calculation. What's going on here? Right, so it only asks us to compute t. We're not asked to calculate the curvature, so we don't need as many steps. T is defined to be r prime over magnitude of r. Okay, that's the definition. Yes. So we take the time derivative, each of these component functions. We get minus 4 sine t, 4 cosine t, and 3. That's right. And then dividing it by the magnitude. So we see that that's expressed below. We would have to square each of these guys and then take the sum and then take the square root. And so if we compute that mentally, this is going to end up being, well, the sine squared and cosine squared will simplify together. We'll have a 16 in front. So we end up doing 16 plus 9 in a square root, which maybe I can just write that down. It ends up being 16 plus 9 in a square root, which is equal to root 25, which is 5. So that's why we end up getting this this 5 in the denominator. So really this denominator is just dividing by, we're just dividing by 5, and then we just pass that scalar into each of the component functions, which gives us this as our final answer. So, okay. That's quite sensible. Yes, and here's another example. So yeah, this one, I remember this one. I had to modify. I was only able to modify the numbers of your problem because this it's hard to create something similar, I believe. So this problem is one that I think forces you to use. Uh, you kind of cannot use this expression. At least I tried to, and it became messy, and I don't think it's very. It's not easy. It may not even be possible to do using this formula. I had to use this second formula. So, um, right, using this formula, right. The one comment I had to make about this. So cross products are supposed to work with vectors in three-dimensional space, but the function, this curve, is defined in 2 dimensions. So what we do is we treat the two-dimensional space as being like sitting inside the three-dimensional space. We just treat this as being living in the xy plane, and we set the third coordinate, the z coordinate, equal to 0. So we end up extending this by 1 dimension. Just put a 0 there. Next, we have to take 2 derivatives in order to begin calculating this expression. So first derivative, straightforward, I think. Second derivative should also be straightforward. Just gotta make sure that you know when to insert negatives. Right? Derivative of cosine is minus sine. And then we take the cross product on top. So we're taking the cross product of this vector with this vector. Now I've kind of, I haven't shown all of my steps, all of my working out. I would recommend if you're not able to do it mentally, then you should definitely work it out yourself. Just make sure that you get the same results that I do. I'm beginning to take for granted that you know how to take a cross product. But it is definitely a computation, and I might begin to suppress it, but that doesn't mean that you should make sure that you know how to compute cross products. When you take this cross product, you're going to get zeros for the x and y components, and your z component is the only thing that's going to have stuff in it. It's going to show up from these two functions times these two functions. So this main diagonal times the anti-diagonal. Yeah, it's actually the zeros that are making these guys equal 0. And well, this simplifies, right? Sine squared plus cosine squared, you can factor the 6 out. So sine squared plus cosine squared is equal to 1, so you get 6. Okay, so that ends up being the cross product. And we're supposed to take the magnitude in the numerator. Well, that's pretty clear. The magnitude is 6. So we get that on top. Now for the bottom, let's see. We're taking the magnitude of this guy. So I think I just inserted that in. Is that right? Yes. So you square the components and add them together. That's that. But then with the magnitude, you're supposed to take a square root, and then you can notice that there's a cubed there. So I've combined those two into the exponent 3/2. Okay. So this is an expression for curvature of this curve, and yeah, in parentheses, this curve it's given to you that this is an ellipse. Hopefully that's also something that you could spot. When these two numbers in front of cosine and sine, when these are the same number, you're parameterizing a circle. When they're different numbers, you have a squash circle, aka an ellipse. So in this particular case, what this is actually saying is that the ellipse, you can actually easily get some of the points on the ellipse. At t equals 0, it's going to be the point 3, 0, and at the point t is equal to pi, it's minus 3, 0. And you can do the other right angles. So at pi over 2, you should get 0, 2 when you plug in, and at 3 pi over 2, you'll get 0, minus 2. And so you can connect these together, and that's going to form ellipse. You don't have to draw it, but I'm just trying to illustrate for you. So this curve defines an ellipse, and we're interested in the curvature at the time t is equal to pi over 6. So that's why we take this expression and we evaluate at pi over 6, which we can actually do. You could, in fact, do this by hand. It's maybe a little bit bothersome, but the value pi over 6 is a special value, so you should know sine and cosine of it. Um, these are values that are on the circle. And some simplifying will give you this quantity. So your problem is very similar to this. You'll have different values. I don't know if I switched sine and cosine or not, but I definitely changed this quantity. So, but the process is the same. So yeah, not too bad. All right. And then I think this is the last little bit that I want to mention. So, in other renditions of this class, this topic comes into play. So just for completeness sake, I wanted to mention this as well. So there are these things called the normal and binormal vector that with the tangent vector, this forms something called the Frenet frame, which I didn't mention here, but it's a convenient reference frame for things that are traveling in space. Like I have this image in my mind where like there's like a rocket that's traveling off, and then there's the spiraling coordinate system that is sort of moving along with the trajectory of it, where everything is at right angles. So the important part of this construction of the normal and binormal is that it gives you a coordinate system that is orthonormal. It's meaning that these basis vectors are orthogonal to each other. So the binormal is perpendicular to the tangent and the normal vector, and they're all of unit length. So it creates a convenient coordinate system for objects that are moving in space. It's like a moving reference frame. But just to talk through the construction. So assuming that you have a tangent vector, so maybe I should have mentioned it, but you should actually have this, right, a unit tangent vector. Starting with that, you can produce the normal vector by taking the time derivative and then normalizing it. That's going to give you another vector. It would be better if I had an illustration of this. I don't really want a coordinate system, but say that we just had some particle. So that would be the tangent vector. And then how the tangent vector is changing perhaps would be like in that direction. Does that make sense? I mean, in this picture, it kind of looks like it's going to go this way. And then, so maybe this is the tangent vector, and then this would be the normal vector, and then lastly, you'd have somewhere pointing somewhere, you'd have the binormal vector. And all three of these are supposed to be perpendicular to each other, which you can see by this formula. So the fact that we end up taking the cross product in this order forces us to have a reference frame that is orthogonal. Everything is perpendicular to everything. Yeah, and the final remark here is because the normal vector and the tangent vector are unit vectors, the binormal vector is going to be of unit length as well. Or unit vectors. I mean to say unit vectors. So t and n are both unit vectors by construction. See that we normalize them in their definitions. So they are both unit vectors. Then when we take the cross product, well, one of the properties of cross product, as you know, is that the magnitude of the cross product is the area of the parallelogram spanned by the two vectors. Well, because these guys are by definition going to be perpendicular to one another, the fact that they are perpendicular is because to define n, we take the time derivative. So that means that it's pointing in a perpendicular direction, these two. So these two vectors are perpendicular to each other and of length 1, which means that the parallelogram spanned by the two is going to be a unit square. And so the magnitude of b is also going to be square. Or the magnitude of b is also going to be 1, I should say. So yeah, t and n are unit vectors, and so is b. So this forms what the fancy term is an orthonormal basis. Okay. Yeah, and in other class other runnings of this class, you would be given exercises to actually compute T, N, and B for simple curves, aka things that either lie completely on the plane or helixes. So, all right, I guess that's all I have for this topic.